Hello, everyone. The title of our work is Transformer-Based Tooth Alignment Prediction with Occlusion and Collision Constraints. Next, let's introduce the work of this paper. First, the research background and significance. At present, many manual tasks in the field of stomatology can be replaced by computer technologies such as virtual modeling and deep learning. However, there are still some tasks, such as the design of orthodontic plans, where existing automated technologies are still immature. The method proposed in this paper addresses the above pain points and provides a more comprehensive and efficient orthodontic prediction strategy. The goal of this study is to first predict the ideal post-orthodontic tooth position model based on the initial tooth position model obtained after oral scan segmentation. Next, let's discuss the relevant domestic and foreign research works. First, there is the tooth alignment prediction algorithm TANET, which was proposed earlier. It uses PointNet to encode point clouds, employs a graph neural network to extract and transmit features, and regresses the transformation information of teeth. However, its problems are quite obvious. Its loss function is relatively simple and does not consider the medical rationality of teeth. Later, a team from Shandong University improved TANET by using tooth landmark key points, adopted DGCNN to extract point cloud information, and proposed a three-layer graph neural network structure for hierarchical feed transmission and extraction. However, this method has a problem. It relies heavily on the accuracy of landmark prediction. If the landmark annotation is inaccurate, the overall performance of the network will be greatly affected. Another relatively mainstream method is TADPM, proposed by a team from Tsinghua University. It uses a diffusion probabilistic model to gradually denoise and learn the orthodontic prediction process, and they also incorporated patch information encoding, achieving good results. Nevertheless, its issue lies in that the diffusion denoising process is overly complex when applied to the pose normalization of 3D point clouds, which consumes a large amount of computing resources and time costs. The later proposed TAPOSNet method has problems such as insufficient training data, a basic loss function, and low prediction accuracy. Next, let's introduce the tooth alignment prediction algorithm proposed in this paper. This is the detailed design diagram of the network, which is quite complex. Let's directly look at the simplified flowchart. The network architecture of this paper is divided into two feature extraction modules that combine global and local features. First, let's introduce the core of this network, the SWTBS module. It consists of multiple improved ST blocks, which perform gradual feature transmission on a per-tooth basis. Data is shared among the ST blocks. For example, the position and posture information of a tooth will affect the positioning of other nearby teeth. This module can gradually iteratively amplify data features and also avoid slow training convergence caused by feature abstraction. We also improved the ST block module by increasing the movement frequency and displacement amplitude of the sliding window in the first dimension, aiming to enhance the information transmission and interaction between different teeth within the window. Similar to SWIN v2, we also adopted a post-normalization strategy to maintain the deep structure of the network and improve the network's generalization ability and expressive power. Regarding the two feature extraction paths, the upper global module uses tooth center information with positional encoding, inputs it into the aforementioned TBS module, and the output result is denoted as FC. For local feature extraction, the entire tooth point cloud is directly input into the improved ST block pipeline. Features are extracted using a sliding window and a hierarchical downsampling mode, and the output result is denoted as FT. After merging the two features, they are input into another TBS module for further feature transmission. Finally, a linear layer is used for downsampling to regress the transformation parameters of each tooth. Applying these parameters to the initial jaw model yields the final predicted tooth positions. The aforementioned SWTP is an improved multi-level feature fusion structure where feature merging is performed at each stage. Different from previous structures, we keep the number of tooth channels unchanged. That is to say, during feature merging, only the dimension of the number of tooth point clouds is merged, while the dimension of the number of teeth remains unchanged. This is because the rotation and translation to be predicted finally are for each individual tooth, so there is no need to change the dimension of the number of teeth. This paper also proposes a method for point cloud serialization based on the simulated dental arch line. The color temperature represents the sorted labels. After sorting, it can be seen that the tooth point clouds show obvious color temperature regularity changes in the local z-axis and y-axis directions. The purpose of this approach is to allow points in the same order of different teeth to represent the relative positions between teeth. For example, here, the points in the red box at the beginning of the data are visualized on the jaw point cloud as shown. If the end of the data is selected, the visualized position should be at the most labial side. In this way, a single point can basically represent the relative position between teeth, enabling the window to better learn the intertooth positions when sliding. We also perform data correction on the simulated dental arch line after data augmentation. For example, here, after ordinary data augmentation, we separate the intertooth collisions and pull back the excessively deviated teeth. To explore the optimal degree of data augmentation, we conducted ablation experiments using two methods: ordinary augmentation, training phase, and constrained augmentation, pre-processing phase. Uh, we adjusted the proportion of data obtained from constrained augmentation in the dataset, carried out ablation experiments with different proportions of augmented data, and obtained the results as shown in the figure. This paper also proposes two loss functions for occlusion optimization and introduces the concept of occlusion projection range. In the top-down projection, the overlapping area between the upper and lower jaws is the occlusion projection range. The closer the shape and area of the occlusion projection range of the prediction result are to those of the ground truth, the more correct the upper and lower occlusion is. The other is the occlusion uniformity loss. Within the occlusion projection range, the more uniform the distance between the corresponding occlusion points of the upper and lower jaws, the more accurate the physical force-bearing mode of tooth occlusion. These two methods are used to guide network training. These are the effect diagrams of our tooth alignment prediction. It can be seen that there are 6 cases in total, and for each case, the tooth positions from left to right are the initial, predicted, and ground truth ones. The boxes in the figure mark 4 types of originally problematic areas. It can be seen that problems such as misalignment are solved after prediction, and the result is basically consistent with the GT. We also compared the tooth alignment effects of other methods using the same set of complex data. The column marked with the red box shows the effect of the method proposed in this paper. It can be seen that our method is the closest to the GT in handling scan defects, incorrect occlusion, and triangularly arranged teeth. This is the error distribution of each method. The outermost orange line represents the method in this paper. It can be seen that for our method, the proportion of prediction results with an error less than 1.25 is as high as over 90%, which is the most stable among all methods. Finally, let's move to the conclusion and outlook. This paper mainly focuses on the digital orthodontic plan in stomatology, proposes a fast, efficient, and accurate neural network for tooth alignment prediction, and combines it with a point cloud serialization strategy, as well as new occlusion loss and data augmentation strategies to achieve high-precision tooth alignment prediction. The algorithm in this paper also has some aspects to be optimized. For example, it is necessary to improve the serialization accuracy of twisted teeth. In the future, closed tooth models can be used for training to improve accuracy, and an iterative process can be adopted to predict the tooth alignment steps. Additionally, our dataset contains 837 sets of dental data, which are derived from 3D models of the upper and lower jaw teeth constructed via oral scans. Each set of data includes the dental crown, the tooth closure model, and the transformation matrix of each tooth to its target position. This dataset is now publicly available on the Zenodo platform and can be accessed by scanning the QR code on the right. That's all for this presentation. Thank you all.